Hello guys, today we will discuss about Booth's multiplication algorithm. Uh, it's different from traditional algorithm. Uh, first we shall discuss the traditional algorithm. Assume we had to multiply two numbers m and r, right? So what you'll do is add m r to itself r number of times, right? This would be our traditional algorithm which we learn in schools and during primary schools, right? Another will be the long multiplication method. So there are you multiply digit wise. So let us discuss in binary. So let's say m has some digits m1, m2, let's say m2, m1, m0. It's a three bit number, and r is a two-bit number, r1 and r0. So you know that you will multiply this, so you'll get m2 r0 here, and m1 r0, m0 r0 here. And similarly you can multiply this, you leave this position, the long multiplication method, which we also learn uh, in our earlier schooling years. Okay, and then you'll just add it, right? You'll just add this both, you'll add this both, you'll add this, and then you'll get the final answer, right? So this would be the long multiplication methods. So Booth's multiplication method is a little different. We What the key idea here is, let's say you have a number m, uh, and you have to multiply it with a some consecutive number of ones, right? There are some consecutive number of ones here, and you have zero, and it is embedded some consecutive number of ones are there. Let's say you just have this number, you have to multiply it with this number right here. So you can write it as m times the 2. This is the zeroth power of 2, first power, second power, third power, fourth power, fifth power, right? So it is the sum of the power set. So you can write 2 to the power of 5 plus 2 to the power of 4 plus 2 cubed plus 2 squared plus 2, right? This would be the multiplication. We'll multiply it, right? This would be your original answer. Now you can simplify it, as you can see that it's a geometric series. So you can also simplify it, and you can write it as 2 to the power of 6, that after 2 to the power of 5 2 to the power of 6 minus 2 to the power of 1 here, right here. So effectively it has a consequence of turning this one five terms and four additions into just two terms and a single operation. It's a subtraction operation, but we know that we can perform subtraction with addition using some two's complement or one's complement, anything we, whatever we like, right? uh, so it's, and also you can achieve this intuitively, like after this, if you add some if you add a, uh, number equivalent to the least significant bit, a number whose least significant position is set and rest all are unset bits. So you see that the carry propagates left side, and you get a 1 to the next side, you get a 1 to the next significant bit of the original multiplicand. Okay, so this will be equivalent to multiplying 1 m times, let's say 1, and there are 1 2 3 4 zeros, right? I can write 4 zeros, and effectively here at the ones place I have minus 2. I can write here minus 1, right? Minus 1 and a 0. So it is effective of multiplying to this number right here. And we know that multiplying directly to a 2's power is very simple. You just left shift the number, the uh, time, how many times the power is there. So m, some number m times 2 to the power k is direct consequences. You shift the m, you left shift m k times. You do this k times and you have this result. You have this result. Okay. It's similar to multiplying to a power of 10 in the decimal number system. You just add number of zeros at the end of it. Similarly, you add that many number of zeros at the end of the number. That can be that's a very simple process, and doesn't require any much of computation, right? So this is the key idea behind it, behind the algorithm. Now, how do you even detect, like, so as you can see that we, okay, before that we'll discuss that how can generalize it. So we have this chunk of ones, right? So if, let's assume we have a number r and it has some chunks of ones, like it's zero, and some, it has some ones and some zeros, followed by some another ones and zeros. Okay. So how do you come on to detect this is a chunk of one and this is another chunk of one? Because after detection we know that it's very simple, right? Because here the position doesn't matter. I can name this as some y, and I can go x times, so this effectively y plus x, right? I have x digits, I have x time x number of ones here. So and it is at a position of y, right? So it's just y plus 1, y plus 2, so on up to y plus x. I can generalize it. And here I can do uh, y plus x plus 1, because it will be the next significant bit. And here I want the least significant bit. So this will simply be y, right? So the position doesn't matter, right? So I'll go. And how do you detect this? So simple idea comes through is a simple, if you can build a simple sequence detector, right? What will be the sequence? So anytime, uh, when if you start looking from the least significant bit to the most significant bits, anytime you encounter a chunk of ones, it should start with a zero, right? Start with a zero, it would climb up to the one, it would stay constant at one, then it would come down. So effectively we can find the slope. Effectively we can find the slope here. So how can we find the slope? uh, Instead of finding the slope, we can just see that if we are at a zero and we encounter a one next to it, this should definitely mean that it is a start of a new set of ones. Even if there is a single one, we can even if there is a single one, we can treat it like a chunk of ones. So in this case the x will be equal to 0, right? The In this case we consider here the x would be 0. So uh, here, if there is a 0 followed by a 1 from the least significant bit side, we know that it's a start. It is a start, and while there is a 1 1, we know that we're in the middle of the ones. Okay, so we are in the middle of the chunk. And how do we know that it's an end? So if it's a 0 1, like it's a 1 followed by a 0, we know that it's ending there. Simple, right? And the zeros, if there is 0 0, then that means that we are just at a chunk of zeros. That doesn't matter, we won't bother looking for it. So this is simple, right? But also, if it's in middle, we don't have any use, because effectively it's just turning the all the middle ones into zeros, right? All the middle ones are turned into zeros here. Only the start and end matters for us. So we'll just look at start and end. So how you go about devising an algorithm, stepwise algorithm for it. So we know that we need mine m. Okay, we need m. Of course, we need m. If you have a number m, we need m. Also, we need minus m multiplicand. We need minus m because we are effectively turning this negative, and we'll use 2's complement for that. We'll discuss why 2's complement is easier. 2's complement is easier. That is just an implementation detail. You can also use 1's complement, but you have to take care of the final answers for that. Uh, in that matter, we'll use 2's complement here, and you need to have another number r because you have to multiply m times r. Okay. Uh, so let's go with an example here. And okay, and also let's say m has x bits and r has y bits. So we know that product p would have x plus y bits, right? The product p would have x plus y bits. Okay. So we shall start p by making it 0. We have zeros. These are x plus y zeros because we want x plus y bits here, right, on the p. And then we start with r. Okay, we start with r. Now we look from least significant bit side to the r. uh, Now actually we can have this situation also, right? Like the least significant bit is 1. So how do you know you are starting a chunk? So there is a simple method. We can just add a 0 here. So you can see that we will check the 2 bits. When we check 2 bits, we are checking this bit, the next bit, because we have effectively added this bit. If we have a 0 and a 1, it's like incrementing, and we can go to our algorithm and use the start of the chunk. And eventually, as we move to the left, we see uh, we keep on dividing it by 2. Okay, let's start with here with an example. Let's say r is 7. So we'll have 0 1 1 1. Okay, this is the 7 in binary. Let's add a 0, append a 0 to the least significant bit side. So when you start looking from here, you see 0 1. So let's also keep a counter k handy. It would be handy, and start it with a 0. Okay. Now we look at 0 and 1. We know 0 and 1, start. So you will have start as k. K here is 0. Okay. So we have the starting bit is 0 bit here. So it's effectively seeing this bit. Okay. uh, then what we do is we have to shift to the left to look at it, right? So shifting to the left is the easiest. We can just divide it by 2 or just delete this bit. So if you delete this bit, we are looking at these two bits right now, 1 and 1. So we know 1 and 1, we are just in the middle of block, it doesn't matter. We can increment this k from last step, it doesn't matter. So we just ignore this and increment k again. So increment k again to 2 and delete this bit. Again we have 1 1, increment k again, because 1 1 doesn't matter for us, and delete this bit. Then finally we have 1 and a 0. So 1 and a 0, uh, we should be sure that we are looking at the 0th bit right now, because when the two bits we are looking at the second bit among the two of them, right? So we are looking at the 0, and we are at k is equal to 3. So 0 1 2 3, we are at k is equal to 3. And we know that end would not be 3, like it would be 3 minus 1, right? So the its end is k minus 1, but we shall not use that. We shall keep the end as k. We shall denote it as k only. We'll see that, as you know, because we need this plus 1 here, right? Because if m is multiplied by some chunk of ones, you can convert it to m times 1, 0, 0, minus 1 and 0. So the 1 effectively comes at the next bit. So keeping this as the end is more useful than keeping the true end of the chunk. So we'll keep this as the end only, sk, right? So now we can formalize it, we can generalize the algorithm. So after creating this, we shall start with our first step. What would be our first step? First step would be append. Okay, so initial steps. Before going to the algorithm, we have to do the pre-computation. Pre-computation would be append r with 0. Append r with 0. Okay, this would be our first pre-computation. Second pre-computation will be make product p all zeros x plus y bit. This would be our second pre-computation. Also, we have to calculate minus m, means m dash. Let's say m dash. That's 2's complement of m. This all would be our pre-computation. Before jumping into the algorithm, we have to calculate this because we would need this, right? So jumping to the algorithm, we'll start by looking towards R. So let's say we'll see, look at two least significant bits, of R. Let's say let's call this R dash. This whole appended R of R dash. So when you look at two least significant bits of R dash, there will be different cases, right? First, it can be either 0, 0 or 1, 1. In both the cases, we do. It doesn't matter. We don't do anything. Okay, we don't do anything. We do nothing. Also here in pre-computation, we also make a counter k, which starts at 0. It would be the position counter for the product P where we are right now. It will be clear during the algorithm why we use K. So the next would be 0, 0, 1, 0, 0 or 1, 1. Okay. The next will be the start. What will be the start? Start would be 1, 0. So if it's a start, we know that if it's a start, we have to add negative 1, negative m, right? So you have to add negative m. So you can also write this thing as, if I write this here, I can write this m times 2 to the power of x plus y plus 1 plus minus m times 2 to the power of x, right? I can write this like that. So I'm just adding minus m times 2 to the power of x. Now here, mm, if this thing is there, we just uh, we know that at the start we won't have 1, 1 anytime, right? We can have a 0, 0 or a 1, 0, right? So we just add, if we have 1, 0 at some position, we just add minus m at that position, this x position, right? Xth position. If we have on x position minus 1, and similarly on x position we have start of the chunk, right? We are starting at x position, so we add minus m on that position itself. So let's say we have counter k, so we'll add m dash, that would be 2's complement of m on kth position. Of what? Add to what? We have to add to the product P, right? Kth position of product P. So and, and then if we get uh, the end, next case would be the end. End would be 0 1, right? If the end is 0 1, we know that we obviously defined the end as k. So the kth position is the position we have to add the m, right? So you'll add m on kth position again of p. So these are the cases. After doing that, we have to look at next position r. So for that, we can simply write r r dash, right. Shift r by single bit, right? Shift r by single bit. So or you can write r dash is equal to r dash divided by 2, because it's effectively the same thing as dividing by 2. Then again you look at r dash. So the third would be, uh, you do you repeat you repeat 1 and 2 until r dash becomes 0. You repeat 1 and 2 until r dash is 0. And finally, when r dash is 0, we don't have anything to multiply to. So finally, the product P would be equal to m times r. Let's see it as an example that would be more clear. If we see it in an example, let's take an example of 7 times 3. So we know that 7 in binary is 0, 1, 1, 1, and 3 in binary is 0, 0, 1, 1. Uh, Now, actually, it doesn't matter which one of these we take as m and which one of these we take as r, because we know that product multiplication is commutative. But for an example, we know that r, it's better if we have bigger chunks of 1 in r. This chunk, the bigger it is, the better it is, right? So we, by observation, we see that 7 has a bigger chunk of ones. That's why we would take this as r. Generally it won't matter, but just for our simplification in this an example, we would use 7 as r, and 3 as m, right? So we have m that would be equal to 0, 0, 1, 1. We are starting the pre-computation is, we have to calculate r dash, right? So r dash, we have r dash is equal to, append a 0 here, so I have 0, 1, 1, 1, and a 0 extra. Okay. Then it's p, I have to calculate p. I have product p is equal to 4 plus 4, we have 8 bits, so I have 8-bit number, that would be 0, all zeros. Okay. We have this p. Next we have to compute m dash. M dash would be 2's complement of this thing. So we know that 2's complement is, we flip the bits and add 1. We flip the bits and add 1 here. So this is the 2's complement of 3. But there is a twist here. If you do this, you won't get the correct answer, and this 2's complement is totally wrong. Why? Because in our algorithm we see that we are adding m dash to p. We are adding m dash to p, And clearly m dash is a 4-bit number and p is 8-bit number. So we have to calculate m dash also in 8 bits. We should calculate m dash in 8 bits, then only we can claim it to be and uh, real 2's complement of 3, right? So we have to because we are adding it to p, that's why we have to calculate it in 8 bit. Similarly, m should also be 8 bit, but because all the most significant bits are 0, it doesn't matter. But in m dash, the significant bits won't be 0, they would be 1, that's why it matters. So we'll calculate in 8 bit. So all this that were 0 will become 1, with the most 4 significant bits. And then we'll have one more 1 0. Oh, sorry. Would have 1 1 0 and a 1, right? We flip and add 1. So you can check this. This is all. This is 2 to the power of 8 minus 3. It's still 2's complement, but in 8 bits. It's still 2's complement, but in 8 bits. Okay. I hope that's clear. So next pre-computation would be k. We'll take k. We'll make k as 0. Okay. So now start with our algorithm. Look at two least significant bits of R dash. Two least significant bits would be these two, right? These two. These two significant bits. We have 1 0. We have 1 0. Add m dash to kth position of m. Kth position would be 0th position. Add m dash to the 0th position. Where at 0th position, add m dash to that position. How do you add to that position? You just align the least significant bit of m dash on that position. So I'll write here all of them are 1. I'll add, so I'll get new p is equal to 1 1 1 1 1 1 0 1, right? This is our new p. Okay. uh, then next next yeah, next you have to do this shift r. So you just delete this bit. So you'll have effectively this. Uh, okay, we just forgot here. And increment k. Just do k plus plus. Increment k. Okay, increment k. So k will become 1. Right? Then repeat 1 and 2. Repeat 1 and 2. So you again look at two least significant bits. Those are 1 1. And we know that if 1 1, we don't have to do anything. We don't do anything here. We just delete k and delete r again and increment k. So we will delete r and increment k, right? Then again there's are again 1 1. Again we will just delete r last least significant bit and increment k. Okay. Then what? Then it's 0 1. Okay, that's interesting. We have 0 1 0 1. Add m to the kth position. We have k is equal to 3. So kth position 0 1 2 3. At third position we have to add m. So our m is 1 1 0 0. Just to fill in, I'll add one more 0. Then I have to just add them, right? I'll get 1 here. This is different. I'll get 1 here. I'll get 0 here. I'll get 1 here. Okay. Okay. I had 1 here. I'll get 1 here. I'll get 1 plus 1. I'll get 0 here and a carry. Then again, I'll get 1 here and a carry. And the carry would propagate. I'll get 0, 0, 0, and an overflow. We knew that we would get an overflow because we are adding to the 2's complement. And we know that when we add to the 2's complement of a number, we generally get an overflow. So we just ignore that overflow, and right, we would ignore that overflow. Okay, we have done this step. Next is divide r. We'll divide r by 2, and we see that r dash has become 0. We have seen that r dash has become 0. So our final answer should be this thing right here. And indeed, that we have got p is 10101. So that if you calculate is 16 plus 4 plus 1, that would come out to be 21 in a decimal, which we know that 7 times 3 is equal to 21. uh, Now, as we know this algorithm, we can directly implement it in Verilog, because in behavior modeling, because we know the algorithm, and we can easily pre-compute these things, and use a for loop and a while loop, loop or a while loop here, to devise this algorithm right here. And we can go about calculating p. So also we notice some things, that the wider the the x and y, the greater they are, the more efficient this algorithm is. What are x and y? You ask. X and y are the bits of m and r. So the wider the x, m, and r are, the more efficient this algorithm will be. And to have the maximum efficiency, we would expect that there should be the largest chunks of ones. Largest chunks of ones. The larger the number of chunks of ones we have, the more efficient this algorithm will be, right? And it also works on signed numbers. It also works on signed numbers. Like if you have to multiply minus 4 times times 5, so you would get it as minus 20. Because finally what we are doing is, if we have minus 4, we just have to make sure that we take the 2's complement of the number in the proper x plus y bit format. We need to take it in x plus y bit format, then only we'll get the correct answer. Otherwise you would just fall in this trap right here, because if we do not if we take this as the 2's complement, then we won't get all these ones right here, right? And that would be wrong. That would be just equivalent to 8 and 6. That would be just equivalent to 14, and not minus 3. So we just have to take these keep these precautions in mind, and we can easily multiply two numbers using Booth's algorithm. Thank you.